Welcome back to Cypress Academy Wicked Wi-Fi 101. Let's get back to it. In the previous videos, I showed you how to create and use a TCP/IP socket with the Wicked APIs. That's cool, but you'd better get some security for your IoT customers. Big picture, in the world of IoT, you need to do two things to have security in your communication. One, you need encryption so that you're sure what you send and receive can only be read by you, the client, and the server in the cloud. The second thing you must do to have a secure connection is to ensure that you know the identity of who you are talking to. And I'll talk more about this problem in a later video. The first part of the security problem, how to send and receive data securely, is handled with encryption. At this point, encryption is basically a big, nasty math problem. And there's a bunch of people out there who've gotten PhDs working on it. I'm not going to get into that at all. And quite frankly, you don't need to, because the world of encryption is divided up into two simple areas. On one hand, you have private key, sometimes known as symmetric key encryption. On the other hand, you have public key, which is sometimes known as asymmetric encryption. We use both of them inside of Wicked, and I'm going to tell you about how that works. First, private key encryption, or symmetric encryption. This system works by both sides of a connection having to know a secret key. To perform an encryption, you take your unencrypted plain text data, or binary data, but it's not encrypted, and you combine it mathematically with the private key to create encrypted data. This scheme is awesome in that it's easy from a computation standpoint to perform the encryption as well as the de-encryption. But it's really hard computationally to unencrypt the data without the key. There's a bunch of these private key schemes, including AES, Triple DES, Blowfish, etc. Here's the cool part. You don't really need to know about the algorithms because the ones that matter are already built into Cypress tools. So what's the problem with private key encryption? The answer is simple to say, but hard to solve. How do you get both sides of connection to have a shared private key without ever sending it over the internet where it could be discovered or eavesdropped on? The answer to this question is really super cool. It's called public key encryption. Public key encryption was created by a crazy mathematical genius. It works like this. There's a pair of keys. One is named the public key, and the other one is named the private key. You can publish your public key to everybody, and anybody can use your public key to encrypt data with. But only your private key can unencrypt the data that was encrypted with your public key. This means if you hide your private key, nobody can unencrypt the data that was encrypted with your public key. Anybody can send you a message that only you can read by encrypting that message with your public key. These public/private keys always occur in pairs. The other attribute of a key pair is that it doesn't matter which one you call public and which one you call private, because data that's encrypted by one can only be encrypted by the other, and vice versa. One thing I will add, and it should be obvious, but I'll say it anyway, keeping private keys private is really important, because if someone discovers the private key, then the whole system falls apart. This is one place where Cypress excels. Our security supports really private keys. So what's the problem with this public key encryption? The answer to that question is that it's computationally expensive to do unencryption with public-private keys. You would not want to have to do this on a low-powered IoT device all of the time. So how do you solve this problem? It's simple. You use public key encryption to exchange a symmetric key. And then all of your exchanges after the original exchange are done with that symmetric key, which was held private by the public key encryption. The system works like this. A client attaches to a server. The server sends the client its public key. The client then creates a big random symmetric key. The client then encrypts the symmetric key using the server's public key. The client sends the encrypted key over the connection to the server. The server then uses its private key to unencrypt the symmetric key. From that point forward, all future exchanges happen with this symmetric key. There's several ways to make this whole scheme more secure, and in fact, Wicked implements those for you automatically. There is one more weakness called the man in the middle, which I will talk about in the video after next. Now that you know the basics of making a secure connection, what do you do next? You make secure sockets. This was originally called SSL, or Secure Socket Layer by Netscape. More recently, it's called Transport Layer Security, or TLS. That's what the S in HTTPS stands for. How do you do that on Wicked? On the client side, you modify your socket code to call Wicked TLS init context after you Wicked TCP bind the socket. Then you call Wicked TCP TLS enable right before the Wicked TCP connect. And voila, magically you have a secure socket. Of course, all of this assumes that you are talking to a server on the right port, one that supports secure sockets. As always, you can post your comments and questions in our Wi-Fi developers community, or you're welcome to email me at alanhawes@cypress.com or tweet me at AskIoTExpert. Thank you.